Kia ora. Welcome to lecture 2 for this week. We're going to continue our study of inhomogeneous linear differential equations. We're going to do the method of variation of parameters. Now this is a little bit more difficult, but it has two huge advantages compared to the method of undetermined coefficients. The first one is it works for any right-hand side, and the second one is not just the right-hand side of those simple forms like a polynomial. And the second one is it works for arbitrary coefficients on the left, so not just the constant coefficient one. So what we did last time with the undetermined coefficients, that was really a very, very special case. Now there's an interesting or very instructive piece of calculus we're going to do here. Quite a clever piece of calculus, which really repays attention. So I thought I'd try something a bit different this time and sort of present it as a commentary on the textbook. Normally, if I was doing this in class, in a lecture, I would do every step on the whiteboard. I could write that out, of course, on the screen, but since there's so many formulas, I thought I'd try it this way instead and see how it goes. So, we're going to take a completely arbitrary second-order linear inhomogeneous differential equation. So these coefficients in front of the y's might be functions of x, not just constants. And we're actually going to end up at a formula for the solution, for the particular solution. And for that reason, it's very important to put the equation first into its standard form. So that just whatever the leading coefficient there, a2 of x, just divide through by a2 of x so that you get coefficient of 1 in front of the y double prime, and you're in your standard form. And the coefficients are going to be very important, and the right hand side might change as well when you've divided by a2. So to make sure you're using the correct right hand side, you must have the equation in standard form. Now, what do we do? Well, we know that the homogeneous solution, or the complementary solution, it looks like c1 y1 of x plus c2 y2 of x. And now we're trying to find yp. So let's suppose that we've already solved the homogeneous problem and found y1 and y2, and they form a fundamental solution set for the homogeneous equation. And the clever idea of variation of parameters is to take these things which were constants in the homogeneous solution and make them into functions of x. In other words, we're going to say, can we find functions of x such that u1 times y1 plus u2 times y2 is a solution? So this is a much more sophisticated guess for the solution because it's actually got unknown functions in it, and it's got so much freedom because it's got two unknown functions and we're only trying to solve one equation that we will see we can actually use that freedom to simplify things and actually solve the equation and find the particular solution. So here's the fun bit of calculus that I want everybody to follow along, and good idea to repeat it for yourself so you can double check everything. So here we go. Yep, too big. Okie dokie. So we're going to have to differentiate this twice. And so you notice they're not writing u1 of x anymore, they're just writing u1. So you have to remember now that u1 and y1 and u2 and y2 are functions of x. And this is a product, so we're going to be using the product rule. So I get, for y prime, I get u1 y1 prime plus y1 u1 prime. Second term times the derivative of the first term. Same thing for the second term. Now when I differentiate twice, each of these four terms has to be differentiated by the product rule. So when I differentiate this one, I get u1 y double prime plus the second term times the derivative of the first, y1 prime u1 prime. So those two terms there go with that one. And then it's the same thing. The derivative of this one is these two. Everything else follows the same pattern. Just have to be a little bit patient and careful. So good idea at this point just to pause the video and check or do it yourself that you get the same derivative. Now comes the good step. We have to take y, y prime and y double prime and substitute them into the differential equation whose left-hand side was y double prime plus big py prime plus big qy, supposed to come out to equal to f of x here at the very end. So here's my differential equation on both sides of this humongous equation. Now what they've done here, they've done two steps at once in order to limit the amount of number of equations. They've substituted this in, but they've also grouped terms together in a certain way which is going to cause this whole big complicated expression to simplify. Okay, so what you want to do is double check that when you substitute these things into the left hand side, you get what they've got here. For example, the y double prime term gives me 1, 2, 3, 4, 5, 6, 7, 8 terms, and they're all in here. But what they've done is they've gone along, and everywhere where they saw a term with a u1 in front, they've factored out that u1. They've grouped all the u1 terms together in here. So let's see where that came from. We've got u1y1 double prime, that's that guy. All the way along, there are no more u1s. Then I have p times y prime. That gives me p times u1 times y1 prime. That's what's here. Then I have plus q times y. That gives me q u1 y1, which is what I've got here. Same thing for u2. The whole formula has a symmetry between the 1s and the 2s. Now the reason for doing that is, look at this expression, y1 double prime plus y1 prime, sorry, y1 double prime plus py1 prime plus qy1, that's equal to 0, because y1 satisfies the homogeneous equation. So this whole term is 0. That's really good. Same thing with this one. It already even says 0 there. Okay, so that got rid of 6 terms, so that's progress. Now we do another very clever thing. We look at these two terms. y1 times u1 double prime plus u1 prime times y1 prime. Now those two terms, they're actually the derivative of something coming from the product rule. This is the derivative of y1 u1 prime. Just check that by differentiating with the product rule. First term times the derivative of the second term gives me y1 times u1 double prime, that's that term, plus derivative of the first term times the second term, y1 prime u1 prime. So those two terms combine into this single term here. Same thing with the number 2's, everything else stays the same. That's the second clever step. Now, here I have a derivative of this thing plus a derivative of this thing. Derivatives are linear, so I can combine those two steps. And now I notice another pattern. In here I have y1 u1 prime plus y2 u2 prime. And here I have y1 u1 prime plus y2 u2 prime. So that will be used, this should be the next thing coming up. They're going to add another equation. Just assume that I'm only interested in solutions where y1 u1 prime plus y2 u2 prime is 0. Why do you do that? Well, one reason is it simplifies this equation enormously, because that whole term is 0, and since this term is 0 for all x, its derivative is 0 as well. This simplifies it down to just 2 terms left. But you're allowed to add that extra equation that you appear to have just made up out of nowhere, because you've got some freedom left, because you've got 2 unknown functions, u1 and u2, and you're only trying to solve one equation. So I take this equation and I add it into my mix here. Then what's left from the actual differential equation goes in there. 2 equations and 2 unknowns. Now it looks a bit funny, but it is in fact 2 equations and 2 unknowns, because you have to remember that y1, y2 and f are all known. This is a linear system so this is 2 linear equations in 2 unknowns. And the unknowns are called u1 prime and u2 prime. So it looks like a differential equation, which it is. But if I just temporarily think of it as an algebraic equation for u1 prime and u2 prime, I can solve that. If I wrote it as a linear system, I would have y1, y2, y1 prime, y2 prime times u1 prime, u2 prime equals 0 f of x. Two equations and two unknowns, you can solve it, and here they write the solution using determinants. So this is Cramer's rule, if you remember this from 102. Or you could just eliminate the variables and solve for u1 prime and u2 prime. That's the other way of getting it. But the formula for the solution then comes out to be this thing. u1 prime is minus y2 times f of x, which was your right-hand side of your differential equation, divided by w. Now we've met this guy w before. That's the Wronskian of y1 and y2. So w is y1 y2 prime minus y1 prime y2. And we know it's non-zero because y1 and y2 form a fundamental solution set. So I can divide by it. And where do they write the solution? No, they don't, so I'm going to write it out again. Summary is u1 prime is minus y2f over w. u2 prime is y1f over w. And that's the formula we're going to use for the solution. Why is this a formula for the solution? Well, everything on the right-hand side is known. It's a known function of x. So this says the derivative of u1 is a known function of x, so u1 is just the antiderivative of this function. Now, because this is a little bit more complicated, when you actually do one of these problems, you don't start with this guess by varying the parameters and do all of that calculus again. You just use this formula here. Plug into that formula, integrate it, and you get the solution. Actually, they say that specifically here. It says, usually it's not a good idea to memorize formulas. You really want to understand what the method is. But in this case, we're going to separate out those two things, understanding how the method works and then actually using it, because it's got a few extra steps there. Okay, I think that's the end, and then they'll go on to do some examples. So they're going to do an example. I won't do the same example. I'll let you look at the textbook. In this one, the right-hand side is a polynomial times an exponential. So this one could have been done by the method of undetermined coefficients. Yeah, that would be one possibility. But instead of that, I'm going to do a different example. Whoa, what's happened here? Instead, I'm going to do a different example. I'm going to do y double prime plus y equals tan x. So that's a more complicated function on the right-hand side. So I could not possibly do this one by the method of undetermined coefficients. First, check that the equation is in standard form. Yes, it is, because there's just a coefficient 1 in front of the y double prime. Then find the homogeneous solution. C1, in this case, is cos x plus C2 sin x. That means my guess for the particular solution is going to be a function of x times cos x plus another function of x times sin x. And that means from the preceding derivation, I know immediately what u1 prime is. It's minus y2 times f divided by the Wronskian, and u2 prime is y1 times f divided by the Wronskian. What is the Wronskian? It's the determinant of your two solutions, being taken care to keep them in the same order. So cos sine, derivative of cos is minus sine, derivative of sine is cos. That is cos squared minus sine squared, that's cos squared x, plus sine squared x, that's 1. So the Wronskian is 1, so that's good. F is your right hand side, tan x, so this is minus sine x tan x. And this one is y1, which was cos x tan x. So this is a case where just using the formula is helpful. So that means that u2 must be the antiderivative of cos x tan x. So I still have to do a little bit of work. I still have to do some integrals. How do I do this one? Well, I'll simplify it because I know that tan is sine over cos. So this is the integral of sine x dx. So that is minus cos x. I don't need the plus c because I'm just looking for the particular solution. I just need one solution. That was the u2. u1 is going to be the antiderivative of minus sine x tan x dx. That is the antiderivative of minus sine x times sine x over cos x. That is the integral of minus sine squared x over cos x dx. So this one looks a bit more complicated. How do I do that? So this will happen to you a lot. You'll have to do an integral, and you may have to go away and do a bit of side research or remember all your integration techniques to see what we can do. So let's look at this one. Basically, with a trig function, you want to try to manipulate it until it looks like a standard integral that you know how to do. For example, it might appear in the tables. So I see it's got sines and cosines mixed up, so I'll change it all, and the cos is on the bottom, so I'll change everything to be in terms of cosine, using sine squared plus cos squared equals 1. So sine squared is 1 minus cos squared. So this is now integral of minus 1 minus cos squared x. Now I've got minus 1 over cos x, so that is minus sec x. Sec is 1 over cos. Then I've got plus cos squared over cos, which is just cos. So the antiderivative of cos is easy, that's sine. But this sec function, that's a bit more tricky, and that one is a little bit difficult to do from first principles. So at this point I would just look it up in the tables, and the antiderivative of sec comes out to be the log, natural log of sec plus tan. So this is minus log absolute value of sec x plus tan x. It's one of these little tricks using some trig identities, and plus the antiderivative of cos, which is sine. Okay, so now I know the particular solution. Yp, it was u1 y1 plus u2 y2, so that it is equal to minus log absolute value sec x plus tan x plus sine x times y1. I've forgotten which one was y1 and which one was y2. y1 was the cos. Plus u2 y2. u2 was minus cos, and y2 was sine. Ta-da! There's the solution of the differential equation, y double prime plus y equals tan x. So there's no way you could have guessed that. You need a more systematic method. So this takes a little bit of practice, and I'll leave you to read the other examples in the textbook and then have a go at the exercises yourself. Cheerio.